FCFS first come first served works like a line at a candy shop. The first child that reaches the counter gets served first, and every other child waits their turn in the order they arrived. In a computer, processes called jobs are like those children. When a process asks the CPU for time, it joins a line, a queue. The CPU simply picks the process at the front of the line, runs it until it finishes, then moves to the next one. This rule is needed because the operating system must decide who gets the CPU next. Without a rule, the CPU could pick processes at random, leading to confusion and unfairness. FCFS algorithm is very simple. When a process becomes ready, put it at the tail of a FIFO queue, first in, first out. The CPU always takes the process from the head of the queue. Run that process to completion, non-preemptive. When it finishes, remove it from the queue and repeat step 2. The queue works just like a line of people. New arrivals go to the back and the person at the front is served. No reordering, no priority checks. The order never changes once a process is in the line. Implementation tip: the operating system often uses a linked list where each node stores a pointer to the next ready process. Adding to the tail is O1, removing from the head is O1. 4 common performance numbers are used to judge how good a schedule is. Throughput, how many processes finish per unit of time. For first come first served, throughput equals number of completed processes divided by total elapsed time. Turnaround time, T total time a process spends in the system. T sub I equals completion time sub I minus arrival time sub I. Waiting time, WT time a process spends waiting in the ready queue, not including its own CPU burst. WT sub I equals T sub I minus CPU burst sub I. Response time, RT time from arrival until the process first gets the CPU. For first come first served, this is the same as waiting time because a process runs only once. Average values are computed by summing each metric for all n processes and dividing by n. Average T equals the sum over I from 1 to n of T, a T sub I divided by n similarly for WT and RT. Because first come first served never interrupts a running job, the response time equals the waiting time. Consider 3 jobs that arrive at time 0, 1, and 2 with CPU bursts of 4, 3, and 2 units. Process P1 arrives at time 0 with burst 4. Process P2 arrives at time 1 with burst 3. Process P3 arrives at time 2 with burst 2. First come first served order is P1 to P2 to P3, arrival order. Compute start, finish, turnaround time, and waiting time. P1 starts at 0, finishes at 0 plus 4 equals 4. Turnaround time 1 equals 4 minus 0 equals 4. Waiting time 1 equals 4 minus 4 equals 0. P2 cannot start until P1 finishes, so starts at 4, finishes at 4 plus 3 equals 7. Turnaround time 2 equals 7 minus 1 equals 6. Waiting time 2 equals 6 minus 3 equals 3. P3 starts at 7, finishes at 7 plus 2 equals 9. Turnaround time 3 equals 9 minus 2 equals 7. Waiting time 3 equals 7 minus 2 equals 5. Average turnaround time equals 4 plus 6 plus 7 divided by 3, which is 5.67. Average waiting time equals 0 plus 3 plus 5 divided by 3, which is 2.67. Throughput equals 3 processes divided by 9 time units, which is 0.33 processes per time unit. This simple arithmetic shows exactly how first come first served timing works. Advantages: simplicity: no complicated data structures, easy to implement like a straight line of people. Fairness in order: the first process that comes gets served first, so no one can cut the line. Predictable: once a process starts, it runs to the end, making it easy to calculate when it will finish. Limitations: convoy effect: if a long-running job gets to the front, all short jobs behind it must wait like a slow turtle at the front of a line, making everyone else wait. This lowers overall throughput. No priority: important real-time tasks cannot be moved ahead of less important ones. Poor average waiting time: because waiting time depends heavily on the order of burst lengths, the average can be much higher than other algorithms, e.g. shortest job first. In many modern operating systems, FCFS is only used for the lowest priority queue or for very early boot stages because of these drawbacks. Preemptive scheduling, for example round-robin, shortest remaining time first, can interrupt a running process and give the CPU to another one. Round-robin, abbreviated RR, slices the CPU into small time quanta, for example 10 milliseconds. After a quantum, the current process is put at the tail of the queue, allowing others to run. This prevents a single long job from blocking the line, reducing the convoy effect. Shortest remaining time first, abbreviated SRTF, always picks the process with the smallest remaining burst, even if it means stopping a currently running job. This gives the smallest average waiting time but requires knowledge of future burst lengths. Compared to FCFS, preemptive methods improve responsiveness, lower response time, and average waiting time, but they add complexity, need timers, context switch overhead, and bookkeeping. FCFS has zero context switch overhead while a process runs, while preemptive algorithms incur a switch at every quantum or when a shorter job arrives. FCFS works best when jobs arrive at roughly the same time and have similar burst lengths like a grocery store, where every customer buys a similar amount of items. The system does not need real-time responses, for example, batch processing of print jobs, overnight, or compiling a large code base where jobs can wait. Simplicity is more important than performance. Early bootloaders, embedded controllers with a single periodic task, or teaching environments where the concept of a queue is being demonstrated. In contrast, interactive desktop environments, web servers, or multimedia playback need quicker responses, so they use preemptive or priority-based schedulers rather than pure FCFS. CPU burst variability means some processes need a short burst while others need a long burst. In FCFS, a long burst that arrives early creates a convoy. All later processes, even very short ones, must wait for the long job to finish. This can look like starvation for short jobs because their waiting time becomes large, even though technically every job eventually gets CPU time. If burst lengths are highly unpredictable, FCFS cannot adapt. It treats every job the same regardless of length. In real systems, this can cause poor overall throughput and high average waiting time, which is why many OSAs combine FCFS with other queues, for example multi-level feedback queues, to move long jobs to a lower priority queue and give short interactive jobs quicker access to the CPU.